keynote from Joe. And before I introduce Joe, I really want to make some comments on the logistics. We are really trying hard to make this workshop very similar to in-person setup. So it will be really appreciated if you can turn on your video if it's convenient for you, so our speakers can see the audience. And after the talk, you will have chance to ask questions. You could either raise your real hand, if your video is on, or you could use the raise hand button. Of course, you could feel free to send questions in the chat and I will moderate after the talk. Okay, I hope that I will see more faces on the videos. And let me introduce our first keynote speaker, Professor Joe Emer. Many people in the community know Joe as a great architect, since he has made a lot of research contributions to this community in the past 40 years. I would like to just highlight a few of them, otherwise it will take a whole day. He has made contributions to a number of YArch alpha and x86 processors. He is recognized as one of the developers of the widely employed quantitative approach to processor performance evaluation, which you must have learned in your computer architecture courses. And more recently, he has been recognized for his contributions in the development of deep learning accelerator design. Besides his research contribution, I have to say that Joe is also a great mentor and a role model for many people in the community. I personally have benefited a lot talking to him. I feel like every time I talk to him, I learn something new. I would like to quote from my friend, Chris Fletcher, professor from YArch. He told me that Joe is the Gandalf in computer architecture, which I could not agree more. And Joe has held various industry and academic positions. Currently, he's a professor at MIT, and he spends part-time in NVIDIA. Earlier, he worked at Compact and Digital Equipment Corporation. To be honest, I'm really curious about what Joe will talk about career choices, since he has seen both the worlds. He has been in both worlds. So now let me give the floor to Joe.
Thank you very much, Mangjia. That was a very flattering introduction. Yeah, so thank you very much. I'm actually very pleased to have been invited to give this talk, and I am going to sort of follow on what Mangjia said. That there are a lot of choices that one makes during one's career, and so in previous mentoring sessions, a lot of people have asked me, a set of questions like, how does one decide between academia and industry? How does one pick research projects? How does one approach research projects? And so what I thought I would do is talk about the major factors that I considered over the course of my career in those regards. And so, I want to make it very clear that there are no pat answers to any of these questions of which way or what choice people should make. That everybody has their own priorities and their own things that will make them happy, and it's only a matter of weighing the factors and deciding what's going to be best for you yourself. So to begin, I did my undergraduate at Purdue University, and when I was going to go to grad school, I decided I was going to go to grad school. That was actually almost more in part an economic decision. I happened to be graduating undergraduate during a recession in engineering hiring, and so when I looked around, I said, I got advice, why don't you go to grad school? Things will be better when you finish. Although I had a leaning towards research anyway, so that was a very easy decision to make. So I applied to a bunch of schools. The question was, how do I decide which one to go to? And this was before the days of visit days. And so I actually made up my own visit day, and I visited different schools. And really what swayed my decision was, where did I think I was going to get the best mentoring, and where did I think that I would fit in. And that's sort of summed up in an expression that I heard later, which says that when you make a choice on where you're going to go, after a while, you will start looking like the group that you join. And so here, I give you a picture of the group I joined at the University of Illinois. And actually, when they say you're going to look like them, it's not physically look like them. I don't know that I ended up looking physically like any of them. However, what you will do is you'll end up looking like them philosophically or in style. And so I'm actually very happy that I picked Ed Davidson as my mentor, because he was a fantastic mentor. And I had a fantastic set of colleagues that I worked with there. And the style that he instilled with me is something that's have stuck with me forever. And that is, he was extolling, before it was, the norm, to do detailed modeling, to do quantitative evaluation of your research ideas, do simulation, do modeling. And so that's what I ended up doing. It happened that the research I did was on fine-grained multi-threading. And that will sort of come back in my career much later. But when I finished my PhD, I was sort of the third generation of research work on multi-threading. And I didn't really see it going anywhere, having any impact. And so what I was really looking for when I was going to take a job, one of the things foremost in my mind was actually a desire to find an opportunity to work on real problems and have potentially long-term impact. And so that was, that at the time, that was sort of the foremost consideration, in addition to compatibility and recognizing, even though I didn't know the terms at that time, that I was going to end up looking like the group that I joined. And so turns out that I found an ideal spot in industry. So industry is the place where you're more likely to actually be able to see real problems and look at real challenges that need to be addressed, and potentially have impact on products and see the results of your work. And so I picked industry and I went to digital. The particular group I joined was called System Performance Analysis, or SPA. It was part of the research group there. And it turned out to be a perfect combination for what I was looking for, because it was part of the research group. Their objective was both expanding the state of the art in performance modeling and simulation, but at the same time collaborating with research groups on their problems. And so it was actually, I thought you would be amused. This was the org chart. Everybody in those days used to draw org charts of the organization you were in. And so this was the org chart with all those levels, even for this tiny organization in SPA. I ended up, this was the org chart as when I joined. I ended up being in that lower left group of modeling and analysis. So I joined the group, and a question that one has is, well, how do you pick a project? What project is it that is going to make sense for you to work on? And the advice I have here is, don't obsess too much about the initial objective of your research. A lot of people say, well, I have to pick exactly the right research project. The point is that it's actually difficult to predict where a project is going to take you. And what you have to do is make the best of what that project offers and not worry about exactly what it is. And I take heart from the career of Sir Isaac Newton. So I think we all agree that he was a great contributor. Does anybody know what his initial research objective was? It's easier asking in person. But what I read was his initial research objective was actually to correlate astronomical events with events in the Bible to validate things in the Bible. So it didn't really matter what his initial objective was. The work that he did in order to achieve that is actually where he made his big contributions. So where did I start? Well, one of the projects or issues that came up early in my career was work on it was actually the first development of a microprocessor VAX processor. VAX was the line of processors being developed at Digital Equipment Corporation. And there wasn't enough room on a single chip for both the processor and all of the microcode. And so the question was, and that meant there was chip crossing and a lot of latency and a lot of energy as well, I guess, for getting the microcode instructions for running the processor. And so question was, well, could we put some of them, would it be worthwhile to put some of them on board the main processor? And turns out the answer was, oh, you need this distribution of what's the distribution of uses of the different microcode instructions. However, the point was we didn't have that data. And of course, in development, you need to have the answers to your problem yesterday. So they had to make a guess, but in reality, one can't guess how a complicated system is gonna behave. And I've actually been inspired a lot in my career by this work by Herb Simon, Nobel laureate, who wrote something about the sciences of the artificial, a book called The Sciences of the Artificial, where he points out that human-made systems today are so complicated that you can't just intellectually reason about how they behave. We couldn't reason about how the microcode was going to work, how much microcode we could effectively, if we could put a small amount on the main chip, would that really help us or not? What you need to do is think about an engineering process sort of as if it's a science project. So look at engineering objects as if they are nature, and you need to study them that way. And so that really dovetailed very well with the philosophy that Ed Davidson had instilled into me. And so the next several years I spent in SPA I was working with a development team. They asked the question, I couldn't answer the question. I said, what I'm going to do is build the analysis environment in order to answer that question, even though it's going to be irrelevant to them. And so I spent the next few years of my career doing what we would call quantitative analysis. And so I ended up creating lots of data like this. This is the data that I collected around 1982, looking at the translation look-aside buffer miss rates for both the I stream and D stream. So I had this data, and I was still a very junior engineer, but I had been invited to a big design team with all the DEC senior architects. And they were discussing the considerations for a future VAX design. And they got into this huge argument about how important the TLB was going to be and what its impact on performance was going to be. And they were going back and forth, and I was just sitting there in the audience, really not sure what, not feeling confident enough to speak up. And finally, I finally worked up my courage, and I said, well, I've done some measurements. This is exactly the rate of misses in the existing design. You can calculate what the impact of that is going to be on your design. And the argument just stopped. And one of the very senior architects there said, "Oh, Joel, you ruin all our fun. You have data." And so I took, a couple lessons of that. One was the importance of actually doing these characterizations and, studying systems and understanding them thoroughly. It also works into an aphorism, which interestingly, I've seen attributed to Zig Ziglar. It's also been attributed to, like, the Romans, and that is, success is when opportunity meets preparation. And that is, take your time, do the work that you think needs to be done. Don't worry about the fact that the VAX design team needs to know what the miss rate on a microcode cache would be at the time, but step back and decide what really needs to be done. Take the time to do it. I realize now that I have been focusing largely on sort of a research perspective. One doesn't need to do, even in industry, one doesn't need to do research, and it's not for everybody. I'll tell you why it was important to me, because the other opportunity in industry is to be involved with development. And in development, you get to build a machine and see that machine go out, and maybe it will be the greatest machine in industry. But a long time ago, I read this book. It's still an interesting book by Tracy Kidder called The Soul of a New Machine. It was a biography, it was a history of the development of a super mini computer at Data General Corporation. And as I remember it, there's a scene towards the very end of that book where the protagonist of the story, the lead developer, is watching the assembly line, seeing his machine roll off the assembly line, and feeling very proud that it is currently the absolute pinnacle of mini computers in the industry. And he also realizes that that will probably be true for less than 6 months. And I just thought to myself, and everybody can make their own opinion, was doing something that will be the best in the world for 6 months in and of itself was not going to make me, give me satisfaction. And so it is something to think about, based on the kind of activity that you do. It is very satisfying. I knew that it wasn't for me. The other push that will frequently happen in industry is a push to management. And actually, almost from my first successes in industry at DEC, they're saying, "You're doing great. Won't you manage a group?" And I thought, I didn't want to do this, and that was reinforced when around that time I went to see a talk, and I went to see this talk by the then leader of Microsoft Research. And what he did was he went through a list of all the great things that they were doing at Microsoft Research. So they did this project. And he described, we did this project. He described this wonderful project. I said, "Oh, that's cool." And he says, "And we did this project." And I said, "Oh, that's really cool." And he went through this litany, and I was thinking, wow, that guy's doing some really cool stuff. And then on reflection, I said, "Oh, wait a minute. He's probably not doing any of that. Yes, he's talking about it, but he wasn't in the nitty-gritty nuts and bolts of any of those projects. He was just over it." And so that's another consideration, is, do you want to be, the person overseeing everything, or do you want to be in the nuts and bolts of how things work? And I like being in the nuts and bolts. I like, coding and spending time writing program. I was late to a meeting with a student the other day, and I apologized profusely. I said, "No, I was debugging. I'm sorry. I just was sort of, so imagine." She said, "You were debugging?" Yeah. I want to keep, I want to keep relevant and know what's going on with systems. So that, again, my personal perspective and what I found to be important. So, okay, doing all this data collection, and is the data collection, or is this really important? And what I believe is it's not the data that's important. It's that one should strive for developing abstractions, generalizations, and principles out of it. So, for example, this is the table from my 1985 paper on the characterization of VAX. And this data was used, so the data was actually collected around 1981, 82, was used through many generations of VAXs at DEC in order to understand, what were the design trade-offs, what was the benefits of doing this or that, how important is this feature in the machine or not. In some ways, that wasn't what I think was most important, because the other thing that came out of that work was sorry, I have a build here that I didn't was what my colleague at the time called the iron law of performance. So developed this formula which allowed us to sort of globally understand the performance of systems and roughly categorize the contributions of the architecture, the microarchitecture, the technology and circuit attributes. That allows you to understand better what systems are. And so that notion of getting at the principles behind it rather than just the data is something that I came to think was very important. That got reinforced because at the end of that era where I was doing quantitative analysis, there was a huge reorganization at DEC. And so the organization that I was part of got disbanded. And so this is another characteristic of people's experiences when you go to industry, which is that there is, not always a lot of stability organizationally in companies. And so with this reorganization, I said, well, I need an escape. Ended up, I had an opportunity to become a visiting scientist at MIT. So I actually spent a few years as a visiting scientist at MIT. The project I was working on happened to be involved with networking, not as irrelevant. And so on my chart here, even though I've listed sort of the projects I've worked on over here, instead of project, what I actually got out of my experience at MIT was an appreciation for abstraction. I know a lot of people say abstraction, but it is actually a very deep concept to think about the abstraction of a system and not the concrete characteristics. And so I think that that is a lesson that you should, especially if you're interested in research, take to heart. And somewhat a extension of that is to approach research like science. So if you think about the scientific method, and I have sort of been very heavily influenced by the work of, say, Thomas Kuhn, Nature of Scientific Revolutions, and so that he describes, or my interpretation of how he describes the scientific method is that you make a hypothesis about the behavior of the world. You design an experiment to try and validate that hypothesis. Run that experiment, quantify the results, interpret the results in the light of your original hypothesis. If it matches the hypothesis, fine. But the more interesting thing is when the interpretation of the results do not match the original hypothesis. That's when scientific revolutions happen. and you create a new hypothesis. This is how science advances. So I see sort of a analogy of that approach in the way one should do research. You make a hypothesis about the behavior of the system, but then what you're going to do is pick a baseline design and a workload to run on that design. That is your experiment. You then run the experiment, which in our case is going to go back to this quantitative approach, or the emphasis on simulation and modeling from Ed Davidson. You run the simulation model and measure the hardware if you can. You interpret the results. And now, if the results show something interesting, what you're likely to do is propose a new design that is going to hopefully give you better results or improve something, and iterate on this process. And I ran a number of projects that I believe fit into that model. One of them was the work I did with George Chrysos that resulted in store sets. And what we did was we ran initial experiments on the machine. Target machine found out that there were problems with the way memory dependencies were handled, and that inspired a solution and then iterated again. But it was a matter of, we didn't know there was a problem. We studied the system and looked where problems were, noticed where things did not meet our expectations. So I want to append one other sort of feeling I have about that process, which is, don't slavishly adhere to all of the characteristics of existing systems. I think of this in terms of relaxing constraints. Decide on a constraint to relax in the way your system is going to operate. And I could give a whole talk on different ways to relax constraints, apply the scientific method. And the point is that at that point, revolutionary contributions may arise for a few reasons. One is, maybe that constraint will be relaxed in time. In other words, you just had to wait for time for that constraint to change. In many cases, the constraint wasn't actually fundamental. What it meant was, by you not having to think in terms of that constraint, it opened up your mind to think of different things to do, because you weren't sort of channeled by the way that constraint set things. And so therefore you can retrofit the benefit into a system where that constraint still exists. The other is, in the same line of that, this frees your way of thinking, that new avenues of exploration will be opened up. And so I take very much as heart to, this notion of, do not slavishly adhere to all of the constraints that everybody around you says a system must have these characteristics. You don't have to always think that way. So go back to my history. So at this point, I actually had been part of this group called VSSAD that began at Digital. And we worked on a number of projects that followed, I believe, that model I just described of applying the modified scientific method for research and relaxing constraints on various systems. This is where work on pipelining was done, out of order execution, SMT, including the store sets work that I described. Also, subsequently, was another thing that was inspirational. So I was working with Shubhu Mukherjee, and he was enamored with this notion that if you look at a bit in the system, you say it's a zero. He said, oh no, maybe there will be a gamma ray that is going to come and upset that value and turn it into a one. And systems are going to be affected by this. And he believed this, and he went to management and said, oh, this is important, this is important. And they said, yeah, go away. Yes, we're aware of that phenomenon, we're not worried. And so he came back to me actually, somewhat discouraged. And so what did we do? What we did was we applied the quantitative approach again. So in some ways, I felt that this effort with him was somewhat of a recapitulation of my early work on quantitative analysis for performance, but we were doing it for reliability. Developed the philosophy, the equivalent of the iron law for reliability analysis, built up an evaluation of current systems, and lo and behold, it was going to be an issue. We could project when it was going to be an issue, developed analysis methodologies, the quantitative approach for reliability and analysis for that. So I see this as as I said, a recapitulation of the quantitative approach, but I see in it a message, which is don't ignore the crabgrass. So Shubhu liked to refer to the problem of unreliability or instability in bit values as the crabgrass in the lawn of computer architecture. And so I think that that's important. In fact, looking here at Mongjia, she's looking at the crabgrass as well, and I'm collaborating with her some. So security analysis today is probably the most significant crabgrass in computer architecture today. So continuing my career, I had an interesting experience that Digital was acquired by Compaq. And then my group in Compaq was acquired by Intel. So I ended up working for 3 companies here in the same group without changing my desk. But I continued these kind of work, the reliability work that I described, the vector work, multi-core work, all of those activities were conducted in that group. At that point, I'd say maybe you could say that I had what you might call a midlife crisis. I don't know if it was midlife or not, but I actually, at that point, wanted an opportunity to have more research freedom, to be able to partake of a more academic culture, the kinds of activity that you find in academia, where you have this more, I don't know what the right word is, sort of forward-looking, open-minded environment, where you can relax even more constraints. If you're in industry, there's always going to be a pressure that the work you do is going to be relevant to a product, more likely sooner than later. And in academia, you can think about things that are going to have much longer term impact. And so I actually found an attraction to that. And I also found that I like the opportunity for just learning new things. And I found that I also liked lecturing, educating, mentoring people. And that's something that you get to do in academia. I have been doing it for a while, and I taught the same course for 12 years. And I every year felt fresh, updating the course and learning new things myself, because I'm trying to figure out how to better frame the information in that course. You say, why didn't this occur to you earlier? And I attribute it to a lack of maturity back when I was in college. So when I was in college, as many of you will probably find, you have to TA a course. I TA'd a course, and there were some students in that class who were not doing well. And I'm actually going to mark that. So the result was I joined MIT, but I was teaching this class, and there were some students who were not doing well, did not seem to be interested in the material. I couldn't figure out what they were doing in the class, and I focused on them. And I said, this is no way to spend my life. This would be too depressing. And at the same time, I completely ignored the segment of the students in the class who were excited about the material, who would come by my office because they wanted to talk more about it. They were in, and they did well, and they were invisible to me. And so it's not a surprise, but it is very important to look at the glass as being half full, not half empty. And for a number of decades, I looked at the glass as being half empty, and I realized that that's not the way to do it. So what did I do when I joined MIT? What was my focus? Well, I was sort of inspired by this notion. So I don't know if people remember what this is. You've probably seen pictures. This is an F-117A Nighthawk. It's introduced around 1981, 1983. It has a very distinctive shape. I mean, all these very, hard angles on it. And it was a stealth fighter. And, I always sort of thought that, oh, the stealthiness is because of this odd shape. And then in 2005, the F-22 Raptor was introduced, also a stealth fighter. Where are all the hard angles? They're gone, but it's still a stealth fighter. What was the difference? The difference was in the ability to simulate the effect of the shape of the plane on the radar. And so the difference was better computing, and the difference was the ability to simulate the system better. And so this inspired me to say, I want to be able to do simulation of computer systems better so we can build better computer systems. And so I worked at that time on accelerating simulation systems. And what we did was we built a system based on FPGAs that would be used as a simulator. But here's another example of what you pick as your objective and what you get out of it do not necessarily correlate. Our objective was faster simulation. What did we do? We learned about spatial architectures, in this case, FPGAs, and the need for building a system around it and how you would be able to modularly construct systems. And so we ended up developing a set of principles for accelerated computing, things like based on latency and sensitive designs, based on storage idioms that we could use as the principles for building a system. So that's actually been the basis of much of my latest work. But what is my motivation? So my motivation has been the black swan theory. There's a little bit of divergence. So I don't know how many of you have heard of the black swan theory. It was something that was described by Nassim Taleb in a 2007 book. And what he notes is that many of the most important events in human history have had a set of characteristics. First, and actually most important, is it something that has happened by surprise, that people were not anticipating it. In his book, he talked about World War I, the onset of World War I, the Great Depression, the fall of the Soviet Union. All of these were events that people were not anticipating, but they had a major impact on world history. And he notes a third attribute, which is that the event is explicable in retrospect. And interest in his theory tends to resurrect when something big happens. When we had the 2008 market meltdown, people characterize that as a black swan. The current pandemic has also been characterized as a black swan event. It happened by surprise, has had a obviously major effect, and in retrospect, we should have been able to anticipate that this was likely and been prepared. So these outlier events are very important. What I feel is that there have been a set of similar events in computing. Think back to the early 80s, the personal computer, there was VisiCalc. People building the personal computer did not anticipate doing spreadsheets, but it was developed by VisiCorp, and it had a huge impact on the adoption of the PC. In fact, I think people have argued that the adoption of and widespread adoption of the PC was largely driven by the desire for people to do spreadsheets. It also, in retrospect, you'd say, well, of course, why wouldn't somebody do an accounting spreadsheet on the computer? Other events like the Windows icon mouse pointer interface, again, has that attribute of being huge impact on the market, on the personal computing market. Desktop publishing, similar. Computer graphics. There have been more recently. So Taleb mentions two. One is he talks about the rise of the personal computer as one black swan event. And he also talks about the rise of the internet. Within that, we've seen a bunch more. Web browsers for handling images, audio and music streaming video. What is the underlying attribute of all of these? Every one of these black swan events arose, in my opinion, because we had a general programmable environment that people could innovate on, that we allowed a lot of people to try and program it, and some people came up with really great things. People at University of Illinois with the web browser. Before that, obviously, Tim Berners-Lee, the web browser for text. And each of these has arisen because we have this general purpose computing environment. So what were the attributes of all of these computing black swans? They were based on the availability of a computing engine with the following attributes. The engine provided an abstraction that enabled applications to be compiled to it from a high-level language, so it's easy to use, in unanticipated domains. You could do things that the designers did not anticipate was going to be the function of that machine. And secondly, the engine provided an abstraction behind which implementations could be continuously improved in performance. We kept on being able to build better machines with improved technology, with improved architecture that didn't affect the ability to generate new programs on. Obviously, as we all know, with the end of Moore's Law, we're not seeing that opportunity anymore. We can't just build totally general purpose. And so my motivation has been, okay, can we build some kind of compromise, some kind of system which is not quite as general, but still relatively general that people are going to be able to innovate on. So that's been my motivation for the kind of system I want to build, and I've been looking at spatial architectures. And so to close out my career, I left Intel a number of years ago and joined NVIDIA. I'm in the architecture research group where I've continued this spatial architecture research, also focused on deep learning architecture in that same domain. And now what we're doing is in some ways trying to regeneralize the deep learning architectures into more general architectures. So that's a summary of my career through the decades and some of the considerations that were in my mind as I went through, you know, picking research projects and picking jobs. Open for questions.
Thanks a lot for the talk. It's really a lot of words of wisdom. And sorry about the thing that we just realized that this chat option is not enabled in the Zoom. So, okay, so we could either use the Clouder, which I don't know how you can easily access to that, or you can just unmute yourself. Okay, first raise your hand, real hand, or the raise hand button. Okay, and I will just call your name, and you can ask the question. Okay, let's just do that. Either use your real hand or the raise hand button. And before that, I know that you may need some time to prepare. So maybe I will have the privilege to ask the first question, because I actually have a lot of questions to ask, because it's so amazing to see a great architect to show like what his research interest evolved over the past 40 years. And now it seems like all the projects you have been working on in the past 40 years are getting connected. I would see that how things, how you jump from one to another. And my question is that it seems that every time you work on a project, you spawn something new. You inspired by something when working on one project, and you got yourself into another more exciting project. But not always like that. Okay, many times, not many times, but it is many times. You may hit a project and you realize, okay, it's not as interesting as I expected. Then you feel like it's not really the right project for me, even though I know that we should, you know, do not need to think about things about the initial objective, because we may get different things out from there. But it's just quite common, right? Especially in the initial stage where you do not have a thorough taste, a very good taste of research, you may end up with a not exciting project. Do you have similar experience, or it never happened to you?
So first, let me comment on your first observation. And yes, I do feel that there was a thread through all my projects. There were certain foundational things like the simulation and modeling, and using that as a foundation. It was like, I don't know, maybe you can't go wrong with that as your foundation. And so then the question is, were there some projects that didn't go anywhere? I think there were a few that I spent a little bit of time on. In some ways, that engineering research adaptation of the scientific method allows you to prune quickly, right? So you should always be looking at, you know, what is the upside potential. You run the experiment, and part of the interpretation is, you know, what is the upside? And if there's not any upside, you should abandon quickly. So
yes, that is the motivation.
I don't remember. I may be, you know, looking at history with rose-colored glasses. I don't remember ever spending a long amount of time on a project that went absolutely nowhere. Invariably, there was some, and it's what you said, which is that the next project was often inspired in part by something that I did in a previous project. And so they built on each other. And I'm always using the ideas from earlier projects in new projects, and that just gives me, a head start on how those projects are going to proceed.
I see. It is potentially because that you are always trying to validate that is a real problem. You are always looking for real problems. And if it's a real problem, then you always can come up some solutions and evolve on that. Maybe that is why it generally do not go into a dead end, because that's a real problem.
Right. So you can look at pieces that were dead end. So for example, the FPGA based simulation project, you can think of it as the project itself, you can think of as a dead end. We never really were able to get an accelerated model of any real machine, but we learned so much about spatial architectures and so much about building an operating environment around a spatial architecture that the ideas are still being used today. The other thing out of that was learning a lot about, fine-grained spatial architectures like FPGAs was what inspired the direction to coarser grained. I just realized that there were so many liabilities in trying to use a gate level spatial architecture like an FPGA. That was what inspired my interest in coarser grained. I
see. Great. So nice. And is any student would like to ask a question? Have a question here? Oh, Alex.
Very qualified student. So
we're all students of life forever.
Thanks, Joe. That was a very inspiring talk. Lots of valuable advice here. I was wondering, you mentioned about this approach of constraining, of relaxing constraints. I was wondering if you've also ever tried the opposite of imposing constraints that are currently not there, but one can envision that as technology evolves, there will be new constraints. For instance, leakage might not have been a problem, but down the line, it is a new constraint that, if you're among the first ones to observe, you can solve a problem proactively. Of course, it's harder to convince people maybe by imposing new constraints, but is this something that you've used in your career?
I don't know that I've really used it. Maybe you can think of the reliability analysis as, it is introducing a constraint. I called it crabgrass because, we need to worry about the reliability of the devices to bit flips. But I don't think of it that way. I think that is probably, constraining can also free your mind, but I find more the opposite, that constraining your thinking, adding constraints also tends to channel your thinking. And so I think I've had more challenge trying to convince people to relax constraints. You have to do it. You can't be wild about it. You need to be you need to be, somewhat judicious on what constraint you relax. So that's some judgment. But I think that convincing people of that has been the hard part. So when I first one of the first times I gave the keynote address sort of on that theme, a very senior researcher of the time came up to me afterwards. He's now, he was senior at that time. He's now won the Eckert-Mauchly Awards. He's very, very highly respected individual. And he came up to me and he says, I want to argue with you. He actually said, the only constraint that I can ever see relaxing is the number of transistors you have available. Believe in Moore's law, and that's the only one. He said, but I can't, I don't have time to have that argument with you. I have to go talk to my student who's about to, preparing his talk for this afternoon. So he goes off, and then he comes back to me later that afternoon, and he says, remember that argument I was going to have with you? Forget it. I went up to my student, and the student said, look at how our work fit into that relaxing constraint model. We had a paper before where we ignored a lot of constraints and showed how this technique worked and provided improvement. And this paper is showing how you can reintroduce those constraints into a real system and still get that benefit. So I want to restructure my talk to follow that model. So I had one win where I convinced somebody that relaxing constraints made sense, but I would say that in general, I have more of a challenge, people saying that that's unrealistic to do that.
Great. And okay, maybe our students are not brave enough to speak up, but oh, I see. Okay, I see two. So you are in the queue. Marina, you are first, and Drew, you are next.
Can you hear me?
Yes.
Yes.
Great. Thank you. Thanks a lot for all the insights and the excellent talk. I wanted to ask whether it's possible and what the balance should be between someone working in academia and keeping an eye on the problems that industry is dealing with. Like, is there any chance that someone working in an academic environment, whether a student or a professor, kind of tries to be more visionary and not deal with the problems that industry is trying to deal at this specific point? Or are we just bound to deal with the same problems just with different approaches?
I think the ideal in academia is to look beyond what industry is currently worried about. You want to ground yourself to some extent, and some work is going to be very grounded. But I think that if we look at some of the things that have had long-term impact, it was decades. Sometimes it's been decades before people sort of adopted those ideas in industry. And I think that's where, real contributions are coming from. If it's just an incremental thing, I'm not so excited about it. Like I said, everybody has their own feelings. I was at a faculty tenure review one time, and one of the reviewers sort of said, this person's work is a lot of one-time tricks. I'm glad that he's doing this work, but I'm also glad that I'm not doing it. And so it's reflective that, that different things are right for different people. And I have my biases, and I've described them, but I'm not insisting that I impose them on everybody.
Thank you.
Good. Drew, you're next. It's your turn.
Great. Thanks a lot, Joel, for the talk. And I had a question. So it's great to hear you talking. It seems like everything is linear, super aligned when you were working on different things and all. But to me, I didn't even know you could jump like that from industry to academia. Like, it sounds if you want to become a professor, you need to follow that track where you're a young professor and you work really hard to get tenure and all these kind of things. And so I'm wondering, how is it even possible that you work in industry for 20 years and then you're like, oh, I'm a bit bored, I want more freedom, let's become a professor at MIT, and it just all work out? Like, how is there a thing that made that possible that you didn't tell us about in your talk? Like, were you invited by MIT to become a professor immediately? Like, what is, so I wanted to hear you a bit more about like this kind of transition and porosity between industry and academia.
Okay, so one, I'm sure that the appearance of a linear sequence is ex post facto imposition of something linear on something that probably was not linear, and I'm whitewashing a little bit. I'm not doing that deliberately. It felt linear to me. How did I end up in academia? Well, I did in research, industrial research, you have the option of publishing or not. I published a little bit. I would say that my publication record was not extensive, and the world has changed. Even academics didn't publish as many papers then as they do now, but I published a small number of papers, and they were significant. So I was lucky that I published a small number of papers that were known and that people thought that I had done significant work. And so when I felt this wanderlust, I both interviewed. I had academic offers, and I also happened to talk to Arvind at a meeting and mention my interest. And he said, well, why don't you come teach with me this fall? And so I did. And so then I started teaching and, got an appointment at MIT. I was, again, just very fortunate that my manager at Intel said, oh, this is great. I'm glad to have you spend your time there. Don't worry about it. And so I was able to do both for a long time. I think, as you know, I'm now actually full-time in academia, and I spend just a small amount of time part-time at NVIDIA.
Great. I think it's really the time, so we can wrap up. But thanks a lot for Joe's talk. At least I personally learned a lot from it. And I think we need Alex. We need to transition to our poster session. Okay, anyone who still have more questions to ask, Joe, will you join the Gathertown or not? Maybe they can ask you questions in Gathertown.
I can't join this one. I'm hoping to join the poster session, the second one.
Great. So
later.
If you have questions, you can find Joe in the second poster session.
I hope, but I also will be at the roundtable next week. That for sure.
Exactly. So you got it. Mark it on your calendar, and we have the Gathertown link. So Alex, do you want to do the transition here?